Okay, so it's good to see everyone. Sorry about that snafu trying to get into the room, but we made it and it didn't take too much time, so that's good. Um, okay, so before we get started into the slides, a couple of quick announcements. So one quick announcement is that I made the solutions for the practice final. I'm going to post them, I guess, as soon as I get back to my office during office hours. Um, in the process of writing the solutions, I realized I forgot to give you a number on part 1B, so that part was unsolvable in the original file. So I updated the file on Canvas for the practice final to give you the necessary information to solve. I also went through and made sure that I added all of the physical constants, which is what I plan to do for the actual final. So on that note, if you didn't see my announcement on Canvas, I just want to highlight the fact that you can make a one-page cheat sheet full of formulas and such for the final. I don't anticipate having a formula sheet, so you should bring what you want to use, but I will include constants, so you don't have to put in like all the tables from the book. That would be miserable. But if I were you, I would just go to the summary section at the end of each chapter, look at the formulas listed there, and focus on making sure those are on your sheet. And you can also write notes to yourself about how to do certain things. Hopefully that'll be a nicer way to take the final, where you have a little bit of knowledge that you can draw upon, which I think is more realistic also to what you would do in most real world situations. Anyways, I think those were the main 2 points. I have office hours, the normal office hours today, and then I posted the schedule of office hours for the rest of the week on Canvas, including a time for a final review session. So hopefully that's all helpful. I guess before I start, since there's so many announcements, are there any questions about the announcements before we get into the slides? Yes. No, it can be like if you want to do it, if you want to do it on Word, or if you want to do it on an iPad and print it or something like that, those are all okay. Just the front page of one normal 8.5 by 11 sheet of paper. I mean, if it's like the similar size of the A series of paper, that's okay too. Like whatever the closest one is. I'm not sure, but yeah. So one of those two. Any other questions? Yes.
Covering chapter 20 early solving opportunity.
That's a very good question. We are going to cover the beginning of chapter 20. I'm looking at adjusting the homework accordingly. But I really, so I'm required to teach you about multi-lens systems, and I might even put one of them on the final, but it's going to be very similar to what we're doing today. And I really want to teach you about microscopes because I think you'll all find that to be useful in your future. So those are the two things I really want to do from chapter 20, basically, are multi-lens systems and microscopes. And then on that note, I'm planning on releasing today, due to popular request, a list of all the sections that I think are fair game for the final or anticipate potentially being on the final. And I may or may not narrow it down further when we get closer to the final time. But for now, I want to give you at least the ones that I think are considered part of the course and like potentially coverable. Mm-hmm. Yeah, so very good question. Any other announcement related questions? Okay, so we left off with refraction, and actually the thing we're about to start, which is lenses, is still refraction, but we're just going to do what we love to do in physics and abstract away all the complications. And so even though we're going to be dealing with refraction when it comes to lenses, we won't have to use Snell's law. We won't have to do any of this like really hard geometry that we've been seeing in some of these problems. We're going to abstract that all away, and we'll be left with what are known as thin lenses. So a thin lens is a piece of some transparent material, usually glass, but not always, that causes light to bend. And so based on the curvature of the surface, that changes where the normal line is. So for example, you can see that at this point, the normal line is right here. And they draw this in this lower picture. And so as light enters this lens, it curves toward that normal line. So by changing sort of the size of the circle, the radius of that circle on the front, we can change where the normal line is oriented, right? If we make this a rounder circle, if we make this lens look like this, where it was very round, then the ray hitting towards the top would encounter a normal line that's directed more towards the upper left. But if it were a flatter lens, then a ray hitting the top would encounter a normal line that's almost horizontal. So you can see what we're doing with a lens when we curve the surface is that we're still, using refraction to bend light, but the amount by which we bend the light, which is always determined by an angle relative to the normal line, changes depending on the radius of the surface of the lens. Okay, so I think this is something that's often overlooked and that the book does a decent job of discussing, as you can see from these pictures here, which is that a lens is a system that uses refraction to bend light. And the way that we control that, or one of the primary ways that we can control that, is by controlling the radius of curvature on either side of the lens. If we curve it very tightly, then that will cause the light to bend very dramatically, whereas the other way around will do the opposite. So you can imagine a perfectly flat lens would just be a piece of glass, and that wouldn't cause horizontal rays to bend at all. Right? If we made a lens that was just a piece of glass and we shone horizontal rays onto it, they would just pass straight through because the angle of incidence would be 0 in that case. The rays would be going in the direction of the normal line. So you can see that with a lens, we're often, but not always, interested in these rays that are traveling horizontally, that for a flat piece of glass wouldn't be bent at all by refraction because the angle relative to the normal would be 0. But by adding this curvature, by grinding down, sanding this piece of glass to make it rounded, what we're doing is we're shifting where the normal line points. And by doing so, we are able to bend horizontally oriented rays of light. And the amount we bend them will be dictated by the curvature. And so we're going to get into more detail, actually more detail than the book, by one equation, so not too much, but on how to actually calculate the way that the radius of a lens affects how it curves light. But for now, I just want to mention that qualitatively. And so we can see in this picture, we have this lens right here, and it's taking these horizontal rays and using refraction. So you can see there's refraction happening at each surface. So on the left surface, there's refraction, and on the right surface. And the combination is bending these rays all to, in this case, all to one point. And so the lens here has a couple of names. So the type of lens shown here. So one name for this is a convex lens. And convex in mathematics is just this idea of something being rounded outward, right? As opposed to concave, which is what we'll look in a moment at, which is something rounded inward. The mnemonic most people use is that a cave is like, an inward region in a piece of rock. And so concave structures in geometry are curved inward, whereas convex structures are curved outward. So just for your reference, here's a concave structure. You see how it's curved inward like a cave. Okay, so alternatively though, these lenses are also called converging lenses. And that's because when you shine parallel rays of light at them horizontally, the rays of light converge, they come together at a single point. And this point actually gets a name. This is called the focal point. So it's a very special point where horizontal rays of light will all come together to meet one another. Okay. So in general, there are two categories of lenses. So the one we just saw was an example of a converging, also known as a convex lens. And you can see on the right here, we have a diverging lens. And what a diverging lens does is it, by curving inward, so by being concave, the normal lines are shifted downward. So you can see for the converging lens, the normal lines are shifted upward from the horizontal, whereas for the diverging, they're shifted downward. And so as a result, diverging lenses, when you shine parallel horizontal rays of light on them, cause that light to spread out. And so generally, diverging lenses are much better at making these virtual images like we saw yesterday, where the light is spreading out, but our eye interprets that spreading out light as if it originated at some different point. Okay. And we're going to get into much more detail with that soon. But while I'm thinking about it, I should mention that how do you get parallel rays of light? Well, if we have something like a star, which is a point source of light, it's emitting rays of light in every direction. And so if you're really far away from that point source, then those rays appear to be almost perfectly parallel. So even for the lights in this room, by the time you're sitting down here in your seat, the lights are way up on the ceiling. That's enough time for the rays to be reasonably parallel by the time they reach you. So it doesn't have to be too far, but a really great example is starlight, which is effectively infinitely far away, at least at the level of approximation we're doing here. And so when you look at a star through a converging lens, what happens is that all of that light gets focused onto a single point. And so if you put a piece of paper at this point, you could start a little fire there or something like that. You're concentrating all that energy into a very small area. So if we think back to our definition of power and intensity, like those calculations from a week ago. However, for a diverging lens, if you look at a star through a diverging lens, it'll appear as if the star, instead of being at infinity, is at some closer distance. So our brain would interpret this point as being the location of the star, because it would see that spreading out light and trace it back to where it would seemingly have come from, assuming the rays traveled straight forever. So our brain doesn't realize how lenses work, and so whenever we see light that's come through a lens, it interprets it as if those rays had just been traveling straight and had no change in their direction. Okay, and you see that they label the focal points. So again, for the converging lens, this focal point is where all of that light that was horizontally parallel is concentrated. And you can see that if we measure from the lens to that point, we call this length f, the focal length. And very similarly, for a diverging lens, we have a focal point, which is where the rays seem like they would have originated when we shine parallel light on the lens. So you can see for a diverging lens, this focal point doesn't actually have anything special happening at it. It's just a sort of an artifact of our brain trying to reconstruct where these light rays originated. But we can still define a focal length f. But as we'll see throughout this section on optics, we've had a long time as physicists to try to fine-tune how we write these equations. And so we used to have separate equations for everything, but we can actually combine them all into one equation, which is known as the thin lens equation, which we'll see soon. And in order to do that, we have to call the focal length of a diverging lens a negative distance. So this is very important. So for a converging lens, this focal length will be positive. And one way you can think of this is that for a converging lens, that focal length is a real phenomenon. It's really where the light gets concentrated. Whereas for a diverging lens, one way you can think of it as negative is just that it's sort of to the left of the lens, although there really is a focal point on either side since these lenses are symmetrical. But when we're shining light from the left to the right, the focal point of interest for a diverging lens will be on the left. So we could think of it as being negative in that sense. But alternatively, we could just say that it's not like a real location of any interest. It's just where our brain perceives the light as originating. And so in a way, the focal length or the focal point for a diverging lens is a virtual, like an imaginary thing. It's just where our brain reconstructs the origin. So this is kind of painting a picture. We're going to dive into a lot more detail on these kinds of lenses. But are there any questions about diverging versus converging lenses, what the focal length is, etc.? Yes.
What exactly is the normal?
So if we go back to this slide, you can see it, I think, best if I erase this crappy line. So you can see it best in these two images, but the normal line is perpendicular to the surface. So if this is your surface of the glass, the normal line would be at a 90-degree angle to it. And when we have a curved surface, we have to, if you've taken calculus, we would say we have to find the tangent line to that curved surface. If you haven't taken calculus, I would say that, imagine you're trying to draw this surface by connecting the dots, like in a children's game, then there would be some pair of dots that you connect in the region where that ray hits, and we could think of that as a flat part of the surface. And so we would take a line 90 degrees to that and call it the normal. And the reason we care about the normal, remember, is that way back here, when we talked about Snell's law, these angles, θ1 and θ2, are measured relative to the normal. So by curving the surface, we change where the normal line is, and we therefore change how the light rays bend when they hit the lens. This is the fundamental idea of how a lens works. And now is a fun time to mention, so at least in the Western history of science, lenses were basically invented by the Dutch in like the 15 or 1600s. And, it's a hard thing to make because you need very, very clear glass for it to be workable. But they were revolutionary inventions at the time. You can think of all the things that we just take for granted with lenses, magnifying glasses, binoculars, telescopes. And almost immediately, lenses the Dutch military attempted to classify them because they found it so useful to have a telescope to look at the enemy far away that they were like, we don't want anyone to know about this. But that didn't work at all, and the rest is history. And of course, Galileo managed to buy precise Dutch lenses and make them himself and make the first telescopes, like for astronomical viewing that way. Okay. So when we look at a lens, and this is the topic of section 19.5, we often want to draw what are known as ray diagrams. And I'm going to pull a lot of them from the book because my drawings really suck generally. But I will try to draw some just to give you a sense of what I expect when you're doing these sorts of problems. So when you're drawing ray diagrams, there are 3 principles to keep in mind. So we have a slide for each principle. So the first principle is that, for converging lenses specifically, parallel rays will be focused down to the focal point. And I guess I should have mentioned back on this slide that the focal length f, once you know that number, that's actually able to describe everything you would be interested in terms of a lens. So it's really marvelous that once we get a focal length, as long as we assume that these lenses are thin, if they're too thick, then it gets tricky because we have changes in the speed of light and we have a bunch of, it's hard to say where we're measuring relative to, right? We have 2 surfaces. But if we imagine that those 2 refracting surfaces are very close together, i.e. a thin lens, and that we can sort of measure from those surfaces as one point, then all that we need to describe a lens, the only number, is the focal length. Okay, very important principle. Okay, anyways then, so for a converging light, parallel rays entering from the left will be converged upon the focal point a distance f away from the lens. And you can see we sort of call this position where the lens is located 0, and we're going to measure things relative to it towards the left and right. And so as an example of this, we could draw our lens, and we can always draw this horizontal line. So that horizontal line, nothing will happen to it because it's parallel on the left, and it will inherently pass through the focal point on the right. So we can always draw a line through the middle. That goes for converging lenses or diverging lenses. And then what we can say is, let's say that we had some object here. We often draw objects as arrows because that way we can tell if they've been flipped upside down or not. If we just draw an object as a stick, then it looks the same upside down and right side up. So we lose a little bit of information. But what we can do is we can draw the light ray that's going, remember, we can think of every point on an object as a source of light rays. In reality, that's what's happening is diffuse reflection, right? There's some lamp somewhere that's reflecting off all the points on the object and scattering light every which way. But just think of an object as if it's emitting light rays for the context of this problem. So what would happen to this light ray that travels from the top through the lens parallel? Well, it would get focused down onto this focal point. Okay, so that's the first ray we would draw when we're trying to construct one of these diagrams. So now the second principle is that any ray that passed through that focal point on the left side would become parallel light on the right side. So what we can imagine is, imagine that we had a lens and we put a little lamp at the focal point, so at a distance f. What would happen is all of these light rays would shine upon the lens and they would come out parallel to one another. And so this is a really handy thing. This is something that flashlights do oftentimes, is that they'll have a light bulb or an LED sitting at the focal length, the focal point relative to some lens. And when the light passes through the lens originating at that focal point, it'll come out nice and parallel. And so it's just better for illuminating your surroundings. It's a more directed beam of light rather than a point source that's kind of spreading out radially. So that's a really handy thing to do. Of course, if you want to make a flashlight, you would generally also put sort of a mirror at the back so that you capture all that light and send it towards the direction you're interested in. And then you just package it up right in a thing with a handle, and then you have a flashlight. So these rays aren't as important in a lot of ray tracing diagrams because generally, unless you set up your system in a special way, you won't really have light rays originating at the focal point on the left, which we call the near focal point. But nonetheless, it sometimes is useful to consider that light originating at the near focal point will come out parallel on the other side. Okay. And finally, rays traveling through the center of the lens are not bent, even if they're traveling through at an angle. So this is different than what I said before. So what I said before is that just the special case, this horizontal line will never be bent because, right, the normal is just parallel to it. So there's no Snell's law business happening there. The angles are all 0. But for a thin lens, and this is where the thin part is important, but for all the lenses we'll look at in this class, they'll be thin lenses because otherwise it's really annoying. For a thin lens, even these other rays that are passing at different angles through the center, we can say that they're not bent to very good approximation. And so if we go back to our diagram here, what we can say, so we could follow this line. So it's going to go through the focal point and keep going. We can draw another line that passes through the center point and keeps going. And so then the place where these two lines intersect, this is where the image will form. So we generally call this side the object, so the physical object, and the image is where those light rays come together again on the other side. And so this is what I expect from you when a problem asks like to draw a ray diagram, is you really just have to draw 2 rays. You can draw more if you'd like. You can draw, so let's say that the focal point, the near focal point is here. You could also draw the line that goes through this near focal point, hits the lens, and comes out parallel. So we can draw that one. So now we're using all of the rays we just discussed. And you see that they all intersect at one point. So that's why we only really need 2 of them to define where the image is going to be located. And so that point tells you where, if you put a little projector screen, where you would be able to see a clear image of this arrow as that light travels through the lens. So I'm going to skip ahead actually, just to give you an example of this. So you can see here, our object is this weird thing, neon lampish thing on the left. And there's a lens here. And we have the image being projected onto a wall on the right. And you can see that by putting this wall right where all of those rays intersect, we get a sharp, clear image. So very similarly to this projector screen, if I move this screen forward or backward without adjusting the lens inside the projector, then it would come out of focus. It would look blurry. And that's because when you have a projector, you're relying on the fact that to make this image, we need those rays to come together at the surface of the screen. So if you're a little bit away from that, where they're not quite lined up, that's what our eye interprets as a blurry image. Okay, so back on the topic of ray diagrams. So what you have to do, just to recap, is you draw your lens, you draw in a horizontal line. You can always do that. And you should label where your focal points are, because those are the critical locations that sort of define what your lens will do to the light. And then your object can be anywhere on the left side for one lens. So you always want to put your object somewhere on the left, but it could be within the focal length or it could be outside. So we could have an object right here. That's allowed. There's nothing preventing me from taking a lens and shoving a leaf right up next to it or something. But the light will obviously do something a little different when we put the object so close. So we'll talk about that shortly. But anyways, we draw our object on the left side, and then we draw these 3 rays. So one that starts off going horizontally, and then that will bend through the focal point and keep going. That's the dark red line. One that just goes through the center and doesn't bend at all. That's the orange line. And one that goes through the focal point on the left and then becomes parallel or horizontal on the right side. That's the yellow line. And they'll all come together at one point, and that's where the image is formed. And so you can see from this that I could ask you some really annoying geometry questions and say, okay, based on where the focal point is, you can find some angle theta, and we could propagate that angle theta through this problem. And if you tell me what this object distance is, so how far this object is from the lens, let's call that S, I could make you find S prime using a bunch of terrible trigonometry and geometry principles and all this stuff, right? Sounds miserable. So I am going to make you find S prime, but it turns out there's a very nice way to do it, way nicer than what you would imagine from looking at these diagrams. And so that's the thin lens equation. So the thin lens equation is what's going to allow us to find S prime without doing any trigonometry at all. Technically it's all packaged into the equation and done for us. So we'll come back to that soon. But before we do, I want to show you this professional ray diagram where they drew the most important rays as the dark ones. So you can see there's one here, there's one here, and there's one here. So those are the 3 that I expect you to draw in a ray diagram, but they also drew all the other ones. So you can see really what's happening to the light going through this lens. And so we have an object on the left that's becoming the image on the right. And we have the focal lengths drawn in, F on either side, both the near focal length and the far focal point. We have the object distance S, which is how far the real physical object is from the lens. And we have S prime, which is the image distance, how far the image is from the lens. And they actually also write the height of the object. So you can see here, we have a height H, which is the height of that right triangle. And here we have a height H prime, which is the height of this right triangle. So this is really all a geometry problem. Once you know a couple of these lengths, you can find all the others, including the heights. So those are, legs of right triangles. So they're also something we could solve for. But like I said, once you get into the context of lenses, we abstract away so much of the difficulty that we really don't have to do trig at all. It's all done for us and packaged up into really nice equations. Okay. And so we have an example problem here. And I actually just paste in the diagram for you. So here we have a 4 centimeter diameter flower. So that would be our height H. Well, I think the way that they're doing this, they don't quite say, but I'm imagining that the flower is centered on this central line. Let me grab my notes really quick here. Nope, okay, they're just taking H to be 4 centimeters. And it's 200 centimeters from the lens. So you can see they draw that in here. Our object distance, S, is 200 centimeters. And the focal length, F, is 50 centimeters. And I should note that for these optics problems with thin lenses, there are no constants of nature that we're having to deal with. So you can leave all of your lengths in whatever units are most convenient, as long as they're all the same unit. So if you're working with centimeters, like in this problem, as long as you leave everything in centimeters, you don't have to do any conversions, because there aren't any constants that are gonna secretly be hiding units and mess you up, basically. So then the question is, how far should the plane of the camera's light detector be placed behind the lens to record a well-focused image? And what is the diameter of the image on the detector? Okay, so the way that they want you to approach this problem, let me see here. Oh, wow, that's kind of silly. So sorry, looking at my notes here, since we haven't talked about the thin lens equation yet, what they want you to do is to really just follow the drawing, like looking at the tick marks on the drawing, and estimate what S prime should be. So they want you to actually measure this image distance, which is a little silly. We'll see how to actually calculate it very shortly. In fact, we could just do it now so that we don't waste this nice example. So I'll write it out in more detail later, but the thin lens equation just says that 1 over S plus 1 over S prime is 1 over the focal length. So this is our equation that we'd want to use. I really hate these problems where they're just like, just count the tick marks or something. That's terrible. Okay, so what we can do is we can plug in our S. It's 1 over 200. We don't know S prime, but we do know F. It's 1 over 50. And so when we rearrange and solve, we'll have S prime is 1 over 50 minus 1 over 200. And for these problems, it's really nice to have a calculator because otherwise it becomes such a pain. But you should get something around 65 centimeters. And you can see that this thin lens equation makes these sorts of calculations incredibly easy. We could also have estimated that from this diagram. So trying to measure some tick marks and get an S prime for this distance here. Once we have S prime, they also want us to find the diameter of the image. And so in order to do that, we really just want to use this idea of similar triangles. So we have one triangle here, and this triangle has a height of h and a base of s. And we have another triangle here, which has a height of h prime and a base of s prime. And these two triangles are similar triangles. So this isn't entirely obvious unless you go through the geometry very carefully, but the angles in these two triangles, so you can see the angles in the center, for example, since that line is not bent, are vertical angles, so they would be equal. And since these are right triangles, that tells you that the other angles are also equal. And so since all the angles match, even though these triangles are different sizes, they're similar. They're just scaled up versions of each other. And so in order to find the new diameter h prime, we just rearrange this equation here. So it's s prime h over s, and plugging into this, I get 1.3 centimeters roughly. And so that's showing you that the image here, and you can see from the diagram that this checks out, the image would look smaller than the object itself. So it's shrunken by, greater than 50%, maybe 60 or 70% smaller than it was originally. And so this is what you would often have to do in a thin lens equation. This is very similar to number 4 in the practice final. So I encourage you, after today's lecture, maybe to try out that problem since you've seen how to do it. And we'll do some more practice examples and get into more detail on the thin lens equation. Sorry to jump ahead a bit, but I don't know. I should have noticed that this one was just wanting you to count off tick marks on a diagram. Anyways, so any questions on this example? Okay. Very good, very good. And so what we just used there when we found this new height, you can see that just from looking at the similar triangles, that the new height was the old height times this factor s prime over s. And so we can call this factor the magnification. And that's what this equation is on the left. And so then the only weird thing about this equation is that it has a minus sign in it. And this minus sign is just a way of telling you if the image is upside down or right side up. So if your magnification is negative, then that's telling you that your image is inverted. And we can see that for this previous example, that the image would be upside down like this, and that checks out. Our s is positive and our s prime is positive. So if we plug into this magnification equation, we would get some negative number. And so if m is positive, then that's telling you that your image is sort of right side up. And we'll see some examples of when that occurs soon. But anyways, that's all that there really is to this magnification equation. I should mention that this equation is known as the lateral magnification equation. So it's just what you get when you draw similar triangles in a ray diagram and try to compare the heights of the object and the image. We will talk about an angular magnification equation later, but we'll save that for when we're able to discuss it in more detail. And then you can see this nice example here. This is a little water droplet on a feather. So because of surface tension, right, you can see how you can write a problem that involves multiple concepts here. But because of surface tension, a small water droplet will bubble up and turn into a little sphere. And that sphere has some curvature on its outside edge. And it's also a different material than the air, right? Inside the sphere, there's water, which has 1.33 as its index of refraction. Outside is air, which has an index of refraction of 1. So all that's to say that a droplet of water acts as a lens, as long as it's small enough that it can be curved under surface tension. And we in fact see that this droplet of water is able to magnify this feather, and that this image, it's not flipped upside down. We can see how these lines connect nicely. So this example has a positive magnification, and it's also a magnification greater than 1 because it's enlarged. And we'll talk about how that's able to happen soon, but it's related to the fact that this object, which is the feather, is very close to the lens, so it's within the focal length. But I want to mention while we're here that in order for this to happen, right, we had to have the water be have a curved surface. So if you have like a water bottle or a hand sanitizer bottle, this is a curved surface. So this can act as a lens. And in fact, if you're very careful, you can even start a fire because this is a converging lens using just a water bottle and sunlight. But if you have a flat body of water, that's not going to be a lens. So I don't know. Someone recently was trying to convince me that light, like a pond or water pooling on top of a roof, would act as a lens and destroy the roof material. And I was like, that's not realistic, right? The lens has to have some curvature to it in order to concentrate the light. But anyways, any questions about magnification while we're here? Okay, so then you might ask, what happens if the object is within the focal length? And so that's what these diagrams are demonstrating. So you can see that here, the focal point is this black dot, that's the near focal point. And we shove our object so close to the lens that it's actually closer than that focal point. So our green arrow here is the object. And so what we can do is we can still draw those 3 rays of interest. Okay, so our first ray travels from the object and then bends towards the focal point on the other side, the far focal point. One ray just goes straight through the middle and doesn't bend at all. And then the one that's hard to draw, but that is important to see, is that there will be some ray that comes out parallel, and it will have been coming from an angle such that if it had originated at the near focal point, it would pass through the lens and come out parallel. So we can kind of extend these rays, even if they aren't actually present in some region, we can extend them backwards in order to figure out which ray would actually, leave the object in green and come out parallel on the other side. And it's the ray that would have passed through the focal point if we had extended it, past the object. So that's this top one here. This part isn't. So that's this ray here, which is the hard one to draw. So we can imagine extending a line back from the tip of the object to the focal point, and then continue that line up to the lens, and then say that it comes out parallel. Okay. Because the lens doesn't care if the light actually originated at the focal point or if it's just a ray that happens to line up as if it originated at the focal point. All that the lens cares about is what angle the ray hits it at, and then it'll bend it accordingly. So that's why we can do these shenanigans when we draw ray diagrams. But anyways, so the net effect of all this is that we get these 3 rays on the right side. And when our eye, so if we put our eye over here and see them, it'll trace them back because our eye just imagines that they all traveled straight forever. So it'll trace those 3 rays backwards and interpret this light, interpret this visual information as an image that's located farther away in this case, and that's larger. So this is how we actually get a magnification greater than 1. And additional, right, because it's enlarged. And we also have a positive magnification here because it's upright. So this is an upright image. It's not been flipped upside down. And so this is what happens when we use a magnifying glass. We have to put the object we're interested in close up to the magnifying glass within its focal length. And what happens is the light coming from that object, or that's diffusely reflecting from that object, diverges. So even though this is a converging lens, we put it close enough that it's within the focal length that causes the light to diverge. And our eye interprets that as some bigger thing farther away, which is what you will experience if you go home and look through a magnifying glass. You'll see that it looks as if, so for the case of this keyboard, for example, that we have this bigger keyboard that's farther away than in reality. Okay, so any questions on what happens? So this has all been so far for converging lenses, right? Both this example and these previous examples. So here we put the object farther away than the focal point, right? This S distance here is bigger than this focal distance. And here we put the object distance within the focal length. But these are, so far we've only talked about converging lens ray diagrams. Yes.
So you put in the number for the lens equation and so for S prime, and you get the power negative.
Yes, so we'll do that soon. But you can see that what happens if we have 1 over S plus 1 over S prime equals 1 over F. So let's say our F is 3, for example, and our S is 2, right? So that would make this F length 3, and you can see if we put our object 2 that's within the focal length, then what happens mathematically is that we have 1/2 plus something equals a smaller number, 1/3. So the only way to make that happen is for S prime to be negative. So we'll counter this in more detail, but I'm glad you bring it up and that you notice that, because it's important. So this image length here, since it's to the left, we're going to call that a negative S prime, and we'll discuss how to interpret that in more detail. Okay, but for now we're about halfway through, so let's take our 5-minute break and we can reconvene. But I'll leave this image up if you want to stare into the depths of ray diagrams.
Yes. So it's part of the formula and one of your answers.
Yeah, no. This one is coming more from what we did yesterday. Very good. So this one's related to that critical angle. So I think that's what you were thinking of.
So it's like just a straight curve and then it's just like perfect.
Yeah, so for this part, it's maybe hard to imagine.
Yeah, it's like
That's why I try to say like a fiber optic cable, but we have, like, imagine a window sheet of glass and you shine the light in through the thin side and then it kind of bounces around within the glass. That's what's happening here.
and are we to use like that and with like air?
So here, if the light's internally reflecting, then our N1 would be the thing we're trying to find, because that's where the light is, and our N2 would be there.
Oh, so it's like going from like right down.
So imagine this is the glass, the light's coming from the glass, trying to go to the air, but it gets bent so much that it just reflects back inside. So that's that total internal reflection. So it's like a fiber optic cable.
Yeah, I'm not sure what that was.
I don't think I'm gonna give you a problem exactly like that on the real final, because I think it's a little hard to interpret, but I really wanted to ask you something about this critical angle idea. So that's kind of, and this is realistically a way you can measure the index of refraction of materials, is you can, take your piece of window glass, have a laser pointer, put it on a little protractor so it can change its angle, and measure. So if you shine it in very parallel, then it'll just of course stay in the glass, but you can change it more and more and more, and at some angle it'll barely change in the glass, and if you increase it anymore, it'll refract out.
So what I was like wondering is that it's pointing with like a 36 degrees, like this is like the minimum.
So here's the glass, the ray is coming in like this, and so this would be the normal.
Oh,
So it's this angle stays. But basically it's just the critical, so we can just use the portion.
oh, okay.
Yeah. It's
And then
hard
the
to.
other what? Like, are you using the biggest size?
So you want to use the one for the critical angle. So it's theta c equals inverse sine of, I forget if it's N2 or N1 or.
Oh,
So there won't be another angle because we're trying to find when
the exiting angle is actually 90 degrees. And if the exiting angle is 90 degrees, then it's gonna cause that to bounce.
Is that for like reflection? Critical angles for.
So it's, the critical angle is when you have refraction that's so strong. So if this is our surface, it's refracting light and causing it to bend. It's so strong that it causes it to bend all the way. And when that happens, instead of refracting, it just reflects.
Okay.
Yeah, it's a tricky thing.
Is it going to be like, say this, then you call like that, it's like reflecting, like.
I'll probably just not ask for something exactly
Oh,
like
okay.
this, but it's good to practice with. If anything else, it might come up on a quiz or something. But yes, I would check out that section of the book because you can see it with some diagrams. It's easier to understand. So it's I think 19.2 or 19.3. I think it's 19.3 because that's where refraction is. Just look for that equation that's like theta sub c is inverse sine of 2/1. Read that section and it'll really help.
Thank you.
But you can also email me and I'll try to explain it better.
Okay, so we should dive back into this. But hopefully having a little break is helpful. We now want to draw the ray diagrams for diverging lenses, and it's very, very similar. But for diverging lenses, basically the parallel and the going through the focal points thing happens on the same side, right? So for converging lenses, we have this behavior where if rays start off parallel, they go through the focal point on the opposite side of the lens. That's what it means to converge the light rays. For diverging lenses, what happens is if you start off with parallel rays, they come out the other side spreading out, but we could trace them back and imagine that they originated at the focal point on the left side. So we call it the near focal point. So you can see how in both cases, so if we had a converging lens and we shine parallel rays on it, they go into the opposite focal point. And for here, with the diverging lens, it's basically just that since the rays spread out, we can imagine them originating at the near focal point instead. So it's still a similar idea of equating, parallel rays going through a lens have something to do with the focal point. But for a converging lens, it's the far focal point that's interesting. And for a diverging lens, it's the near focal point that's interesting. So that's how we can draw these rays. So if we have a diverging lens and we want to draw what happens to a parallel ray when it hits it, well, it's going to spread out and it's going to be the line spreading out such that it would pass through that focal point on the near side. Okay, and very similarly, if we have rays coming in, so trying to converge onto a diverging lens, then the diverging lens is going to say, nope, you don't get to converge, you just get to be spat out as parallel rays. So rays that would normally converge onto the far focal point are instead forced to be parallel on the right side. And then yet again, so this is the same for both. For any thin lens, a ray traveling through the center, no matter what its angle, doesn't change direction. It just passes straight through. And this is predicated on the lens being sufficiently thin for us to be able to say this. Okay, so you can see, very similar set of principles. These are the three principles for ray diagrams in the case of a diverging lens, very similar to for a converging lens, just which focal point is interesting is what changes. Okay, so, oh, I guess that was the last slide in this section. So, I want to say there's some problem where you either draw or look at diagrams for diverging lenses in the homework. But if not, we can maybe talk about them some more in some other context. I think there are at least some thin lens examples in these slides that have diverging lenses. But anyway, so now we can move on to section 19.6, which is the actual useful, primarily useful chunk of this, which is turning all of this annoying trigonometry into a very beautiful equation. And that's this thin lens equation. So this is the main equation for all of chapter 19 and for most of chapter 20 as well. You can do a lot of stuff with this. So it'll handle both converging and diverging lenses, as well as spherical mirrors. So all cases are able to be handled. It seems like it would be really hard to handle all of these different optical devices, but they're all describable by this one equation. It's just that we have to learn how to interpret it and how to choose basically the plus and minus signs of things that we plug into it. And so we can see this is a ray diagram for a converging lens, and they've labeled here for us the main components. So we have S, the object length. We have S prime, which is the image length. And then we have the focal length, which they draw on either side. So you just choose one of these, and that's our F. And so they actually show you the geometry in the book. You can kind of get a sense for how you would do it just from looking at this picture, that we have some right triangles. We find the bottom leg of this second right triangle. This is S prime minus F. And we can do a bunch of geometry to derive the thin lens equation, but it's quite tedious, so I'm not going to do it here. Feel free to read that section of the book if you're interested. But like I said, there are some important things that we should know about the plus and minus signs in this equation. So notably for a converging lens, we call the focal length positive. So you can see this left column here is the positive column. Whereas for a diverging lens, we call the focal length negative. And we can imagine that as being related to the fact that when parallel rays enter a diverging lens, they spread out. And so the relevant focal length is the one to the left of the lens in the negative direction. For any object we draw in ray diagrams, we just always want to draw it on the left. And so the object length, if you just have one lens, will always be positive. If you have two lenses, then the first lens can cause the object length of the second lens to be negative. And we'll talk about that. That's the main thing I want to get to in chapter 20 tomorrow. So S will generally be positive always for one lens, and oftentimes even for two. And so the only other sign we have to worry about is S prime. And like was helpfully mentioned earlier, so if S prime is positive, then that's telling you that the image is forming on the opposite side from the object. So if we have an object, light shines through a lens, and we get an image, then in this lens, this is positive, this S prime is positive, and it's a converging lens, so F is positive. So that in this case, everything is positive. However, if we instead have, we could maybe have, again, a converging lens, but if we put the object really close to it, and we have this S be positive, then the light will diverge, and so we'll actually get an image length, which is to the left. We call that negative. So what I like to think about is, the object length, it's natural to put the object on the left in these diagrams. That's how you'll always see it done, and how I encourage you to do it yourself. So we call object lengths to the left positive. The focal length, we first learn about converging lenses. Those are the ones that people tend to feel most comfortable with. Those are the ones with a positive focal length, converging lenses. It's like the natural lens. And then converging lenses, what do? Well, as long as the object is far enough away outside the focal length, they cause the image to form on the other side, and that would be a real image. So a real image is going to correspond to a positive image length. So in the nicest case, everything is positive. that's how I would encourage you to think about the sign, the plus and minus signs of the thin lens equation in the context of lenses, I guess. But you know, in the every opposite case, so if we have a diverging lens, that would be a negative focal length. That's kind of a weirder lens, right? If we have an image, a virtual image forming on the left side, that would be a weirder type of image. So that's a negative image length. And in the very unusual case that we'll see in chapter 20, where the object somehow gets forcibly put on the right in a multi-lens system, that would be a negative object length, but we'll leave that for tomorrow. Okay, so before we jump into an example, are there any questions about thin lens equation and when we call something positive versus when we call it negative? Yes.
I guess so then, is there any way from the equation we can tell if the image is gonna be right side up or upside down?
Yes, you can. That's a very good question. So remember, we have this magnification equation that's negative s prime over s. So what we can see is that if both our object length and image length are positive, or if both are negative, then our magnification is negative, and that would tell you that the image is flipped upside down. But if either the object length or the image length is negative, but not the other, then the negatives would cancel and our magnification would be positive. That's telling you that the image is right side up. So that's why typically virtual images tend to be right side up, because virtual images correspond to the image being on the same side of the lens as the object, and therefore the magnification being positive. So oftentimes when you're solving one of these lens equations, you're going to be using the magnification equation and the thin lens equation together. So I'm really glad you asked. And I think this example we're about to do will involve both of them. Okay, yes.
The F is that positive?
So, yeah, thank you. So up here I was saying if this F is positive, so we're still looking at a converging lens, but if we just put the object within that length, so maybe, maybe this is the focal length here. If we put the object within that length, we would still call S positive. So F and S would both be positive, but S prime would be negative. So this was the case that we saw here. So you can see, I mentioned how this happens mathematically, and you can maybe see it now that you've seen the thin lens equation, that if our F is bigger than our S, then we'll have, some fraction on the left that's bigger than the fraction on the right. So we have to make it smaller in order for them to be equal, which requires a negative S prime. That's kind of the idea. Yes.
Is the focal length just like a characteristic of lens, or like for given lens will always be?
Correct. Yes. So, and that's why I really wanted to add an extra thing here. So we'll skip the example for a moment. So, this is how you actually find the focal length of a lens. And if you did the eye project, then you'll have seen this. So this is called the lens maker's equation, because it's what you would want to use if you're making a lens, and it's relevant in the practice final if you've skimmed over it. And it is something that I expect you to know, even though I don't think it's in the book. I couldn't find it in the book, but I think it's almost any good optics class will teach you this. So I want this to be a good optics class. But basically, if we want to find the focal length, we know that it depends on the material we make the lens out of, because that will affect Snell's law, right? Lenses are just working on the principle of refraction. And like I mentioned at the very beginning of today, depending on how strongly we curve the lens, that will change where that normal line is, which will make our angles different, relative to the lens. So that will also affect refraction. So we need to take into account both of these things when we try to characterize a lens with its focal length. And like you asked, once you've made a lens, if you don't change it, the focal length is just a number associated with that lens. So it won't change. It'll be the same for any problem that you do with it. And so all of that's to say that if we want to find the focal length, we just have to plug into this equation. The only tricky thing that I will note is that let's say that you had a lens like this, where it's curved on one side and flat on the other. So what would happen is this surface is what we would call R1. And let's say that this is like a half of a circle maybe. So in that case, this distance would be R1 if this were actually a half a circle. But in general, as you can see in this picture, R1 might be coming from a bigger circle that we would have to draw that would be slightly farther away. So, in a realistic problem, you would either be solving for R1 or you would have to, or it would have to be given to you somehow in terms of the geometry of the problem. But if we have a flat side, this is telling us something about R2. It's telling us that R2 is infinity. So for a flat side, you can imagine, how do we make a straight line using a circle? Well, we make an infinitely big circle. And if we make an infinitely big circle, we can imagine it starts off this big, and as it gets bigger and bigger and bigger, the edge of it looks flatter and flatter. And so if it's infinitely big, that's just a straight line. And so a lens like this would have an R1 that's just some number, 5 centimeters, and an R2 that's infinity. And so what we could do is we could write for this lens 1/f, and let's say this is normal glass with an N of 1.5-ish. So this would be N minus 1 would be 1/2. And then we would just have 1/R1 plus 1/infinity, which would be 0. And so we just have 1/f equals 1/2R1, and we can cross multiply and find that f is 2R1. So this is an example of how we would find f for some material. And you can see here I had to use the index of refraction, and I need to know what the radius is on both sides of the lens. Yes.
Did they have a different curvature on both sides, and do they also have different total weight?
Nope. So this is the really nice thing. So even if they have different curvature on both sides, there's just one focal length associated with a lens. And that's because whatever light goes through one way and comes out the other, you can imagine you would be able to trace that same path symmetrically. Snell's law is symmetrical that way. So yep, and a lot of lenses actually have only one side curved because it's easier to make them. And then I just wanted to show you how you would actually make this. So I just grabbed this Encyclopedia Britannica picture that basically you just glue a piece of glass to a flat surface, and then you use these tools that swing like a piece of sandpaper basically on a big circle. And by choosing that radius, you can make either a diverging lens on the left or a converging lens on the right, just by making some mechanical system that moves carefully the sandpaper in a circular, or in reality spherical way, since these are 3D objects. But you can do this. I mean, people did this in the 1500s by hand with pieces of sandpaper. It's like, you don't need to get too fancy with it. Galileo was able to view the moons of Jupiter after he literally hand sanded a piece of glass that was way crappier than the glass that you get, in an IKEA picture frame today. So yes. It's hard to see here, but it's the radius of the right side, the far side. So, if we have this lens, then this side has a radius of R1, this side has a radius of R2. And that's a good point. I should mention that for a diverging lens, we call these negative. This would be negative R1, and this would be negative R2.
So what do you mean, like radius of the far side, radius of the near side? I'm having trouble vision.
Yeah, so do you see how in this image on the right here, we're bringing this piece of sandpaper around the lens and causing it to look curved on the top. So this sandpaper is fixed in such a way that it can only rotate along this circular path with this radius. And so if this were the left side of the lens, then this would be R1, this distance from this point to this point. So that's what the radius of curvature means, is it's sort of what radius would you have to fix a piece of sandpaper at if you wanted to, carve it down to that level of curvature. Does that, yeah. Nope. So you can see, like in this picture here, R2 is not infinity. It has some curve to it. So you know, we could use this apparatus and just create a little cushion and flip this upside down and also make it curved on the other side. So, you know, it would work the same way. We would just have to, in reality, you know, if you're trying to do this at home, you'd have to get some like rubbery material to hold it safely. Yeah, I think it's good to know how to make things, even if you're never going to make a lens yourself. I think it's good to see how someone would actually do it. Yes.
Would it be accurate to say that the less curved it is, the bigger R is gonna be?
Correct. So the flatter it is, the closer R is to infinity. Exactly. So, and that's what I mean by this idea that, you know, going back to the very beginning of today's lecture, if we really curve a lens, if we make it very, you know, tightly curved, then what will happen is we'll have the normal line be really shifted, right? If we really curve a lens, that normal line gets shifted farther away from the horizontal. And so that causes more, you know, a greater change in the direction of the rays of light. And we can see that based on the fact that the focal length would get smaller in that case. So as the radius gets smaller on the right side, the focal length gets smaller on the left side, since they're both on the same side of the fractions. It's a little hard to see, I know, in these pictures, but you can see it in this equation on the right here. If you keep one side flat, then by making the radius smaller, R1, it makes the focal length smaller, F, and that would cause the light to bend more, right? So if the focal length, remember the focal length is this distance. So if we make R1 smaller, which means we're curving it more tightly, then this focal length would get closer to the lens. That's the intuition that you should try to build around this idea. Okay. And so I'm actually going to skip this example for now because I see how low we're running on time. If there's popular demand, I can try to do some examples and post them to Canvas, but I don't know how people feel about that. But anyways, I wanted to mention a couple of things that are covered in more detail in chapter 20, but that are interesting to see now, I think. So one of them is power. And so you can see in the lens maker's equation that we have 1 over F on the left side. And so oftentimes we call 1 over F power. It's not the same. I know it's a confusing, terrible name, but people who study optics usually don't study any other kind of physics. So this power has nothing to do with energy. So not related to watts or anything to do with energy. So this power is optical power. So optical power, and it's measured in diopters. I think it's spelled like that. There might be an extra vowel in there. And these are the numbers, if you have to wear glasses like I do, these are the numbers that they tell you at the optometrist that seem very like, what the heck is this number telling me? And most people know that like the bigger the number is, the worse your eyesight is. And so what's happening there is they're actually telling you the power of the lens you need in your glasses in order to correct your vision. And we'll talk in more detail about this. But you know, what's happening is if you have a converging lens, which is what you would wear if you're farsighted, then what's that lens is doing is it's you know, focusing the light at a closer point, and it has some, you know, real image associated with it. And if the focal length of that lens is 1 meter, then we could do 1 over 1, and we would get a power of 1 diopter. However, if the lens focuses the light more closely, we would say that's a stronger lens. It's able to bend the light more. And so that would have a larger power, 2 diopters. However, if it bends the light less, it has a longer focal length, we would say that has a smaller power, 1/2 diopter. And then similarly for the diverging lenses, which is what I have to have in my glasses because I am nearsighted. those have some negative power because they have a negative focal length, right? Diverging lenses, just by definition, by our notational choice, have a negative focal length. So when we do 1 over f, we get a negative power. So I know the lenses in my glasses, I have an astigmatism, so there's a difference, but you know, one of them is around -2 diopters and the other is around -1.5 diopters on either of my lenses. And so by wearing those in front of my face, I, you know, correct the point where the light converges and cause it to converge where it's supposed to, which is on, you know, my rods and cones. And by doing so, I can see you all clearly. And so there's a nice chart here just showing that healthy vision, you don't need a lens in front of your face. So you would need a lens of 0 diopters, which is just a flat piece of glass. And if you're farsighted, you need a converging lens. If you're nearsighted, you need a diverging lens. And so just to show you what's happening here, so these top 2 pictures are different ways that you can be nearsighted, which is known as myopia. And you can see one way is that your eye just has too strong of a lens and it focuses the light prematurely. The other way is that your eyeball is too long. And so even though your lens is normal, it can't quite reach where it's supposed to. And so by adding a diverging lens in front of this, it causes the light to spread out a little bit more so that it doesn't focus until it gets to the back, right? By adding a diverging lens, it's able to get all the way to the back of your eyeball without focusing. And then these bottom 2 pictures are ways that you can be farsighted, which is known as hyperopia. And so by adding a converging lens, we cause the light to converge where it's supposed to, which is earlier than the light would naturally converge based on your eyeball length and the lens in the front of your eye. Okay, and so now hopefully you can understand a bit more when you go to the optometrist about what they're telling you. Of course, there are a lot more details, which you'll actually learn more about hopefully tomorrow when we get into chapter 20, having to do with all of the little corrections, the aberrations, and the astigmatism, all of these complications that make glasses a little bit more tricky. So yeah, we'll leave this here for today since it's already 9:21, but we'll finish up chapter 19 tomorrow and then do a little bit more on chapter 20, and that'll be it for the course. So we're almost done. Just hang in there a little bit longer, one more lecture.